going to start. So
Okay.
we are very happy to have our own Lei Xue. And she's going to talk about the proof of Grünbaum's lower-bound conjecture for general polytopes and strongly regular CW spheres. Take it away.
Well, thank you, Isabella. Thank you for inviting me. I'm really happy to be able to speak to this audience specifically, and I am indeed going to talk about a lower bound conjecture by Grünbaum on general polytopes and a proof of it. Okay, so yeah, for the audience who were in pre-seminar, you're going to see most of the definitions one more time. Hopefully you're happy about it. So we're going to start with defining a polytope. Again, take a finite set in RD and you take a convex hull of it, that's called a polytope. And if that set is F-only independent, then we call it a simplex. And we can define faces of a polytope by the intersection between the polytope and the supporting hyperplane, like this one. And here's another example. And a k-dimensional face of a polytope is called a k-face. And depending on that k, we can give them different names. You're probably familiar with vertices and edges, and those d-1 dimensional faces on a d polytope are called facets. Those are the maximal proper faces of a d polytope. And we have face vector, the face vector that can keep records of the number of vertices, the number of faces of each dimension. And here's an example, a face vector of the polytope that we already saw. And there's one new definition here, which is the vertex figure. So given a polytope and the vertex of it, so here, look at this yellow vertex V. A vertex figure at V is what you get by sliding in a hyperplane like this. That separate that vertex, the chosen vertex V, from the rest of other vertices. And you just simply look at the intersection. The intersection is denoted as P mod V. It's going to be a d-1 dimensional polytope. And the reason why we like vertex figure is that they have the following nice property, which is this really nice bijection between the set of all k-dimensional faces of P that contains the chosen vertex V and the set of all k-1 dimensional faces in the vertex figure. And this bijection is actually quite intuitive. Say, for example, if you look at this edge that contains V in the original polytope, and just look at the intersection between the edge and that hyperplane you use to cut it. That would be this vertex, and it's going to be corresponding to, for example, this vertex in the vertex figure. And it's true for every k. We're going to use this nice property later in our proof. And now we can introduce the main questions. So basically, if you fix the number of vertices to n and you fix a dimension to d, one can ask, what is the minimal number of I faces such a polytope could have? Such a minimal fi for each I must exist. And you can further ask, well, is there a polytope that has component-wise minimum F vector, meaning that it has the smallest, the minimal possible number of I faces for each I. So that's what we call component-wise minimal F vector. And the reason we're asking that is that we know the answer to those two questions are yes and yes for simplicial polytopes. Those are polytopes whose facets are simplices. And that is the famous LBT, the lower bound theorem, proven by Barnett in 73 and Cali in 87, which says a family of polytopes called stacked polytope, they have the component-wise minimal F vectors among all simplicial polytopes. And we know a lot more about this family. So we also know the other side of the story, which is the upper bound theorem proven by McMullen in 1970, which says cyclic polytopes will have the component-wise maximal F vectors. We're not going to define stack polytopes or cyclic polytopes, but yeah, but we know that component-wise minimal and maximal F vectors exist for simplicial polytopes. And in fact, we have G theorem proven by Bilera and Lee and Stanley, which gives a full characterization of all possible F vectors of simplicial polytopes. Okay. So the upper bound theorem actually works for all like general polytopes, but the lower bound theorem and the G theorem are only for simplicial ones. Just want to emphasize that. So our question is still, is still open for general polytopes. You fix dimension to D and the number of vertices to N. And in fact, we know very little about this problem for general polytopes. If N is greater than 2D, then we don't even have a conjecture to work with. It's only in the case when N is at most 2 times the dimension when we have a conjecture made by Grünbaum in his book, Convex Polytopes, in 1967. And we're introducing this conjecture right now. Okay, so the dimension is D, and we have up to 2D vertices. So we say D plus S is the number of vertices. And then Grünbaum conjectured that the number of K faces of such a polytope will be at least this many, this alternative sum of binomial coefficient. And since we'll be working with this formula for most part of our talk today, we're going to give it a name, call it phi K, and in the parentheses, the first entry denotes the number of vertices, and the second one denotes the number of denotes the dimension. Oh, and I got inspired from last week's Andrea's talk that I should include mathematician's picture in my talk. And here's a picture of Branko Grünbaum. He passed away 2 years ago. Yeah, he's the author of Convex Polytope, the classical textbook for polytopes. Yeah, and I quote Wikipedia that he's a great geometer. I heard from Isabella that there are interesting life stories about him, but I didn't learn the details. So here's a picture of Greenbaum, and let's get back to his conjecture.
Do you know who he's on the phone with in this picture?
I don't know. I'm not sure if he was actually on the phone. I thought it was just a pose. But yeah. Okay, we're getting back to Grünbaum's conjecture 53 years ago. So Grünbaum himself proved the case when S equals 2, 3, and 4 in his book. And the case when S equals 1 is, it also holds trivially, right? There's a unique polytope of dimension D with D plus 1 vertices. That's the simplex, and the number of, Fk of a simplex will satisfy this formula. And in 2019, the following 3 authors, Pineda, Villavicencio, Hugon, and Yost, they proved the case when K equals 1. Remember, K is this, notion over here. And that's the case for the edge numbers. And what we were able to show last year was that the conjecture is true. It holds for every dimension D, every S up to D, and for every K. So this phi K, D plus S comma D is indeed a lower bound for all general polytopes. And we're going to prove this theorem for the first part of our talk. And for the second part, we'll try to deal with the equality case. Any questions so far? Okay, so we're going to start. Before proving the theorem, we're going to show this, what I call a key proposition, which says that, so for the key proposition, we don't care about the number of vertices. Let's assume P is just a D polytope. And we pick a random set of vertices of P of size M. So at most D vertices. We label them V1 through Vm. And we're going to show that the number of all K faces of P that contains at least one vertex from this set will be at least this bound, the summation binomial coefficients on the right-hand side. Okay. And here's the proof. Before start counting, we're going to construct the following sequence of faces of P from F1 to Fm, and they will satisfy the following three conditions. So each Fi will have dimension d plus 1 minus I. So F1, for example, should have dimension d. That will force F1 to be P, right? There's a unique d face of a d polytope. And F2 will be a facet. So yeah, and the dimension will decrease one by one. And for each I need Fi to contain the vertex Vi, but not any previous vertices, right? Not any Vj that comes before Vi. So we're going to construct such a sequence by induction. And I'm keeping those conditions on the board. So it's an induction on M. When M equals 1, pick F1 as P, and we're done. If M equals 2, then we can pick F2 as a facet that contains V2, but not V1. And we're always able to do that. So that will be base cases. And then we can apply the inductive hypothesis on this set of M minus 1 number of vertices to get a sequence F1 up to M minus 1, satisfying those conditions above. But we can also apply the same inductive hypothesis on this slightly different set of vertices of the same size. And in particular, to get a possibly different sequence of faces of length m minus 1. And in particular, there will be a d plus 2 minus m dimensional face, call it G, that contains Vm, but not any of these. So if this G actually also doesn't contain Vm minus 1, we could be done easily. But even if it does contain Vm minus 1, it's still okay because we're only missing Fm for now, and we want it to be of dimension d plus 1 minus m. G has dimension 1 higher than that. That will give us freedom to pick a facet of G that contains Vm, but not Vm minus 1. So, and we'll call that facet Fm. That's how we can construct this sequence of faces of P, satisfying these conditions over here. And then we can start counting. So this is what we want to count. And we're going to count this set in the following way. So each time we only count the number of K faces containing Vi, but not any Vj that comes before. And this will be a disjoint union. And for each I, we're going to count this set by counting basically a subset of that. So each time, instead of counting in P, we only count in Fi. And this is still disjoint by our construction of Fi's. So we can write it as a summation. Now we're only counting for each I the number of K faces in Fi containing Vi. And then we use the bijection that we learned when we define the vertex figure to substitute each of those sets by set of all K minus 1 faces in the vertex figure. And the number of those faces will be at least the number of K minus 1 faces in the simplex of the correct dimension. And that's how we prove the key proposition. Okay. And here's an example, but I'm going to skip it. It's quite trivial. So F1 will be P, F2 will be a facet containing V2, but not V1. In this example, there's a unique choice. And then F3 should be an edge containing V3, but not V1, V2. There are two choices here, you just pick either one. Okay. Okay. And before actually going to the main proof, which will be surprisingly simple, we also need some useful formulas about this phi k formula, which we basically get from Pascal's triangle, those famous formulas about binomial coefficients. Okay, here are the three main formulas we want to use. The first one is by plug-in s equals 1, that's trivial. And yeah, when you compare these two, notice that this term s in the original formula only shows up in the very last term. So when you compare phi k d plus s comma d with phi k d plus t over d, the first two terms get canceled, and the difference between, and this difference on the right hand side can be equal to this, I think, by applying Pascal's triangle over and over iteratively. And combining the first and second formulas, we'll get the last one. Okay, now we can prove Greenbaum's conjecture, and it will be an induction on S, recalling that the number of vertices is d plus s. So the base case, or the first several cases, were done by Grünbaum. So all we need to show is that, assuming that the statement holds for all s prime, which is smaller than s, and all dimension d primes, at least s prime, then it also shows for x and all d, which is at least s. We start by picking a facet f. And let's say f contains d plus s minus m vertices. In other words, there are m vertices that's not in the facet f. And all we need is that this m is at least 2. So we can pick any facet that's not a basis where P, the polytope P is a pyramid over it. And we label those outside vertices V1 through Vm. Yeah, I'm gonna keep the picture over here to remind you. And we start counting right away. So this is what we wanna count. The set of all k faces of P will fall naturally in the following two categories. So k face is either a k face of F, or it should contain some outside vertices. Well, if it's a k face of F, then we can apply the inductive hypothesis on F. By our construction, F will have at most 2d minus 2 vertices of dimension d minus 1. And if it contains some vi, then we apply the key proposition. Okay, and that's why we combine fk of p by the sum of these two parts. The red part comes from the inductive hypothesis, and the blue part comes from the key proposition, we just proved. And then we just rearrange stuff. I'm really not hiding any mysterious thing from you. It's just rearranging terms using the formulas we mentioned. And then we will end up with phi k d plus s comma d, which is exactly what we want to show. It's the lower bound that we want, plus a summation, and each summand is this difference between two binomial coefficients. But we know that m is at most s. Otherwise, if you have too many vertices outside, the rest wouldn't be able to form a facet. We just don't have enough. So each summand must be non-negative, and fk of p is at least phi k d plus s comma d. And we are almost done. There's only one small case that's left that we need to deal with. So what if we're unable to pick such a facet f from the beginning? Well, that means that every facet F is a basis, right? Where P is a pyramid over it. In other words, every facet F has a unique vertex outside of it. In other words, every vertex is an apex. And that will force P to be a D-simplex. And now we're really done. Okay, now any question? We're done with the conjecture. Any questions so far? Before moving to the case of equality.
So when Grünbaum proved the first few cases of this, did he not use induction between the steps and just like did each case for S individually? Maybe I got about the indices or the variables.
He might use, so in his proof, especially for the last one, when S equals 4, there are, I believe, 4 to 5 cases that he was looking at, like different cases. And I think in some cases, he was trying to use induction. And then in some other cases, he counted things differently.
Okay, thanks.
Yeah, so I think, so I was trying to mimic his proof to just prove for the case when S equals 5. And the number of cases increased from 4 that he had to 10. So yeah, I think that if that was what you're asking, yeah, mimicking his old proof was not a good idea.
Hey, would you mind summarizing? Go back to the statement one more time, because just in case anybody got lost in the steps of the proof.
Oops, I didn't want to enlarge anything. Here.
Great, thanks.
Okay, and one would ask, since no one asked, but one could ask that, like, where does this formula come from? It looks very mysterious. Does each term has meaning? Well, I couldn't explain this formula term by term, but the reason Grünbaum believed that this is the lower bound was because he actually had a family of polytopes in mind, which has, yeah, exactly this many of k faces for each k. So he had a candidate, which will make the proof of the equality case quite straightforward. Okay, now shall we move to the case for equality? Okay, let me go here. Okay. Yeah, so we're gonna, so for the treatment of equality, this is our main question. So which polytope will make that this equality is hold for all case? In other words, which polytope will have component-wise minimal F vector? And what if you only ask this equality to hold for some case, maybe not all case? What are those polytopes? And we're gonna go over Grünbaum's construction on the special family of polytopes quickly. So yeah, a pyramid, I guess I cheated already. I used the word pyramid before actually defining it, but usually, but you just start from the d-1 dimensional polytope and add a new vertex that's not in the affine span of the one you started with. So, and you look at the new convex hull, the dimension will go up by 1, and we call that pyramid. And you can do it over and over to get multifold pyramid. Each time you will bump the dimension up by 1. This one more definition. So given the point in RD, possibly outside of the polytope you're looking at, we say it's beyond the facet F if, as in the picture, it's sort of floating above that facet F. In other words, if you look at the supporting hyperplane of that facet, it should have the entire polytope on one side and that point X on the other side. Another way to think of it is to try to look at the polytope from that point X, and that facet F should be the only facet that you could see. Okay, if okay, so it's beyond that facet if you can actually see that facet standing at the point X. Okay, yeah, it's possible that you can see multiple facets. And then there's the definition of dual polytope. So given a polytope P, its dual P dual will be a polytope of the same dimension, but the face poset will be flipped over. In other words, posets, so the facets of P dual will be corresponding to vertices of P and vice versa. Okay, now let's briefly go over Grünbaum's notation and his construction. We start from a simplex. We put a new vertex beyond exactly n facets of that simplex. Okay, try to rotate in the space. So make sure that the new vertex can see exactly n facets of that simplex. And then you'll get a simplicial polytope of the same dimension. And then you just apply a multifold pyramid over this polytope until you reach dimension D. Okay, so in this way, you always get a polytope of dimension D with exactly D plus 2 vertices. It has one more vertex than the D simplex. Here's an example. Starting from a 2 simplex, add a new vertex beyond exactly one facet in this example. So how about here? And then look at the new convex hull. And then just cone over it. Okay. An equivalent definition is the following. If you know the definition of the direct sum of polytopes or joint of polytopes, these two definitions are in fact equivalent. Okay, just in case these mean anything to you. Okay, and we need one more definition. There's a notion called simple. Given a D polytope, we say a vertex of it is simple if it has exactly D neighbors. So a vertex of a D polytope has at least D neighbors. So if a polytope, if a vertex has exactly D, it's having a simple life, so we call it a simple vertex. And if every vertex of a polytope is simple, then we say the polytope itself is simple. This is one of the several equivalent definitions of simple polytope. Here are the other two. We just call them propositions of simple polytopes. So vertex figures at each vertex would be simplex. And given a simple polytope, its dual would be simplicial. Okay, so why would, so the family of polytopes that Grünbaum constructed has many really nice properties. And I'm just gonna talk about 3 lemmas, which tend to be useful. The first one says that, okay, if you start from a D simplex, on the left-hand side, you are adding the new vertex beyond exactly M facets. And on the right-hand side, you add that new vertex beyond D minus M facets. And they will be the same. You'll end up with the same simplicial polytope. And I'm gonna just do my favorite proof by example over here. So in order to get T3 sub 1, you can add a vertex here, right? It's beyond this facet. Okay, and that's what we got. And you can add, in order to get T3, 2, you can add this brown new vertex here. So you can see this one and this one. And now you can turn your head like this to convince yourself that these two polytopes are in fact the same thing. Okay, is it good? Okay, Yeah, they're undergrads here, so I shouldn't say that. It's a joke. You should never prove by example.
Where are the, sorry, where is the brown vertex on T13? Like I see the brown vertex on T23. Where does that go on T13?
So for T13, you're not adding the brown one. You're adding the orange one instead, because you want to add a new vertex that can only see this facet.
Got it.
So it should be right above it, so it couldn't see anything else.
Thank you.
Okay, and there's lemma 2, which says that, in fact, every simplicial D polytope with D plus 2 vertices is one of these. Okay, so together, lemma 1 and 2 should tell us exactly how many such polytopes are there. It should be D over 2, or floor of that, right? Product, we're not using it, just, right there. See, yeah, now you're back. Yeah, okay. For a moment, I think your cameras are all black, but now we're back. And there's lemma 3, which says that for every K, A, and M in reasonable range, we have a nice or relatively nice formula for all such polytopes. We know them, like we know every single of them. We know them well. That's all I'm saying. And if you recall the operations that Greenbaum used to generate such polytopes, yeah, it's not hard to arrive at this formula. So for each operation, I think it's relatively easy to keep track of the F vectors. Okay, and if we plug in M equals 1 and A equals S in the formula above, to compute the F vector of that polytope and flip, because we want to look at the dual, then we get, for each K, is exactly the formula we're looking at. It's phi K D plus S comma D. What this is saying is that we just answered the first question for the equality cases, that this polytope is the winner over here component-wisely. It has the component-wise minimal F vector, and yeah, and for each K, it has exactly phi K D plus S comma D, many D K faces. Okay, here are two winners for S equals 2 and 3 in dimension 3. I include them here because they already showed up previously, so why not? So we can move to the next question. So are there any other minimizers? Are there other polytopes with that equality case holds for some case, maybe, but maybe not for all case? Then we want to go all the way back to the proof of the first theorem and really look at those inequalities to see when they hold as equalities, and have these pictures here to remind you like what those terms are. We can start from this one, which is easier. So for this inequality to hold as equality, we just want this box part to be 0. And that's the case if either m equals 2, so the summation is gone, or m equals s, so this thing is 0, and these two binomial coefficients are the same for each I. Okay, and remember that m is the number of vertices that's not in F. So this will give us a restraint on the size of, or the number of vertices of F. That'll give us the first corollary of the previous theorem. It says that if you want the equality to hold for some k between 1 and d minus 2, then facet should have d plus s minus 2, or d plus s minus 1 vertices, but because there could be like other facets that are actually bases, but we're not choosing them as F, so that's why we have the third option here. Okay, now we look back to this inequality. And for this inequality to hold as equality, we want this box part, which comes from the key proposition, to hold to count exactly what we want in the key proposition, right? We want to go back even further to the proof of the key proposition and see when every inequality there holds at equality. So we go back and remember that, so this is what we need. We need this summation on the right-hand side to be exactly the number of k faces containing some vi. And this is how we counted the left-hand side in the proof of the key proposition. And we actually need the equality to hold for every summand. Okay, so this is what we need to show. And I'm just gonna give you 2 examples to see in what conditions that this equality will fail. So here's the first example, and let's just pick a facet, F. There are 3 vertices outside. We denote them v1, v2, v3, and we start counting, for example, the number of k faces containing one of them. And we will fail in the very first step. So we start from counting edges containing v1, and according to, for this equality to hold, we need 3. But in fact, there are 4, right? You can count. There are 4 edges containing v1 in P. And I claim that this is because v1 is not simple. As long as v1 is not simple, we will always fail at the very first step. So the corollary should be that, well, we need v1 to always be simple. But then we can always reorder those vi's. Any of those vi's could be our v1. So this will tell us that actually every outside vertex should be simple. In other words, non-apex vertices should be simple. But is that enough? Let's look at this example. There's one apex, which is the orange one on top, and every other vertex is simple. You can count. There are exactly 3 vertices, 3 edges going out of each of those bottom vertices. And you can start counting again the number of edges in the way that we do it in the key proposition. For example, you can pick, I think we're picking this facet as our F, so that v1, v3, v1, v2, v3 are the 3 vertices left outside. And we will always fail in the third step. So, and I claim that the reason for that is that this example P prime, this polytope, just has too many facets. When we are counting the number of edges containing v3 but not v1, v2, in the key proposition, we were counting such edges in a d-2 dimensional phase. But in this example, you can actually find better. You can do better. You can find this facet, a d-1 dimensional phase containing v3, but not v1, v2. So you sort of have a spare dimension, and that will like for sure give you more than this many faces at that step. Okay, so let's count the facets that a polytope must have if we want this equality to be true. So we first have this facet that we pick first, F, and there should be exactly D facets containing V1, and 1 facet containing V2, but not V1. And then we shouldn't have any facet left. Okay. That will give us the third corollary, which is the strongest one, I believe. It says that such polytope should have exactly D+2 facets. This will basically do the proof for the equality case for us, because think of it, if you dualize P, it will be a polytope with exactly D+2 vertices. And we just spend like 5-10 minutes on that family, and we know every single thing about that family. Okay, so here's the theorem for the equality case. So if we want this equality between Fk and Vk to hold for some k between 1 and D-2, then the winner we had before was the unique winner. There's no other polytope with this equality holding. And the idea is basically what we had before. So what I just talked about. So by corollary 2, every non-apex vertex is simple. So P is some pyramid over some simple polytope. And this Q basically will share many properties like with P, because basically you're just decoding from P to get Q. And you dualize Q, it's a simplicial polytope of dimension A with A plus 2 vertices. So it must be one of this nice family. And by corollary 1, it also has to satisfy this condition, which will force P dual to be TS sub 1. And that will force P to be our friend over here. And that's for K between 1 and D minus 2. When K equals D minus 1, so the polytope that will make the equality holds, it's in general not unique. So that case is when you fix the number of vertices to n, and you fix the number of facets to d plus 2. So you're basically only fixing the two ends of the F vector. And in that case, as long as you can find A and M satisfying these conditions and this equality, then any polytope of this form will satisfy the equality condition. Okay. I mean, in special cases, for example, if S is some prime number plus 1, then in order to make this equality holds, M has to be 1. And in that special case, this polytope is still the unique winner, but it's just not true in general. Oh, and we can move to a more general setting. So once we prove the Greenbaum's conjecture, we can think of ways to generalize it. And we can think of the following generalization of polytopes, which is a set of strongly regular CW spheres. Those are CW spheres that are regular, meaning that those attaching maps, when you construct that CW complexes, are all homeomorphisms. And plus, you need this additional intersection property such that every intersection of two cells, or just two faces, are still a cell. It could be empty. It just couldn't be more than one cell. And here's some basic facts. So if D is 3, then those two sets are the same. Every strongly regular CW2 sphere actually is a boundary of some three-dimensional polytopes. But once you go up to D at least 4, there are many non-polytopal spheres. For example, Barnett's sphere. It has n equals 8. It's even simplicial, but it's not a boundary of any 4-dimensional polytope. And here notice that Barnett's sphere has D plus 4 number of vertices. And that's important because in order to generalize our theorem or our proof to the theorems to this more general setting, one of the nice properties we're using is property 2 here. Let's change the order. Let's look at property 2 here. So if we only have at most D plus 3 vertices, then they're still polytopal, which is quite nice for us because in our proof for the equality case, remember, we have exactly D plus 2 vertices. So we can still like go back to our polytopal world because of this nice proposition. And proposition 1 says that basically this set is closed under dual. If you have a face pole set of some strongly regular CW sphere, you dualize, you flip the pole set, it's still a face pole set of some strongly regular CW sphere. And stuff like vertex figures or some basic facts that we were using in our polytopal proof before like you're always able to find a facet, including one vertex, but not the other one. Those nice propositions also still hold. So we can naturally generalize our theorems. In fact, the inequality and the equality cases to this more general setting. Yeah, and the proofs are essentially the same. And I think I have 5 more minutes, so I'm gonna go on. The other direction you wanna do to generalize Grünbaum's conjecture is to ask, what if you add more vertices, right? The conjecture was up to 2D. So for vertex number strictly bigger than 2D, unfortunately, oops, yeah, I didn't want to enlarge it. Okay. Yeah, unfortunately, it immediately fails after you add one extra vertex. So if the vertex number is 2D plus 1, we can look at the following 2 polytopes. The first one is what you get by starting from this familiar polytope. You stack over a simplex facet of it, and then you dualize. Okay, this is called the Pentasome in the paper by the 3 authors from 2019. I'll give an example shortly, but we can also look at P2, which is, yeah, also in the same family, Greenbaum's family with exactly D plus 2 vertices, and you dualize. So here's an easy example of a pentasome. You do D equals 3, and we generate, we constructed T D comma 1 sub 1, right? It's this polytope. Hopefully you still remember. And you stack over, you just pick one simplex facet and stack over that one. In this example, any facet except for the bottom one, and you dualize. And hopefully you see why this is so-called pentasome. This polytope in general, P1, will have exactly D plus 3 facets. And that is actually the problem. I'll keep these 2 polytopes on the next slides. So first of all,
Did we lose Lei?
can you hear me? Okay, Sarah, I think, Sarah, can you hear me?
I can hear you.
Okay. Okay, then I'll go on. Hopefully Sarah will be back. I only have 2 minutes. Okay, so first of all, Pineda, Villavicencio, Yugon, and Yost in the same paper that I mentioned before, they showed that for D starting from 5, P1, the pentasomes will be the unique polytope with the minimal edge numbers. Okay, so just look at the red part, not this part yet. What this says is that if we want to believe that the component-wise minimal F factor exists for 2D plus 1, then it has to be the F factor of P1, right? Because it's the unique minimizer in one component. And it's strictly smaller than the number of edge numbers of P2. Although P2, as you can see, only exists when D is even. But on the other hand, P2, the second polytope, has strictly smaller number of facets. So what you're seeing here, right here, this shows that there just couldn't exist component-wise minimal F factor for 2D plus 1 case, at least when D is even. Okay, so that's the bad news. There's still some good news. It's not so bad. So basically, instead of 1 polytope, as that will give you a component-wise minimal F vector, it turns out that in the case when you have 2D plus 1 vertices, those two candidates will be enough. So if you have a D polytope with at least 2D plus 1 vertices, if you know that the facet number is D plus 2, then it's bounded by P1. If the facet number is at least D plus 3, then it's bounded by P2. And the proof for the similar reason can be adapted to the slightly more general setting as well. And I think I'm done just on time.
Let's thank Lei for such a wonderful talk. Any questions?
Lei, would you mind showing that last slide again?
Yeah. Actually, there's a little bit more of it. So we are basically, instead of one bond, one polytopes, instead of using one polytope's F vector as the lower bound, we now have two, right? And if you compare these two, if you compare the F vector of P1 and the F vector of P2, they are, so basically P1 is lower in the first half and P2 lower in the second half. It's quite funny, interesting. And I also want to say that similar things also happen when you have vertex number 2D plus 2. It's just, we also have two candidates and one candidate only exists when D is odd, and things are quite similar. So I personally don't believe that if we have more than that many vertices, then all of a sudden everything will get back to the, will be nice again. I believe that if we have even more vertices, there wouldn't be component-wise minimal F vector. I think that's my belief. I'll be very surprised if up to n equals 3D, everything get back to one lower bound again.
Sorry, can you say what you said again? There's a difference between 2D plus 1 and 2D plus 2. Is that what you said? Or is it that you get new lower bounds as the number of vertices increases even more?
Okay, so I also worked on the 2D plus 2 case, and what happens there is very similar to the 2D plus 1 case. You also have two candidates, call them P1, P2, and they will each, yeah, and together, I believe they will give you a bound, a lower bound. Yeah, polytopes with at least 2D plus 2 vertices. And I don't believe that if you go up, like with more than 2D plus 2 vertices, will you ever be able to get back to something with component-wise minimal, that F vector. Does that make sense?
Yeah.
And I think as the number of vertices go up, we will, yeah, two polytopes won't be enough. You need a lot more. It will get complicated really fast.
But here in this theorem, the P1 and P2, do their number of vertices grow?
No, they have the
They
same
have
number of vertices. Each of
they have
them
a
has
fixed number of
exactly 2D plus 1 vertices.
Each of them has 2D plus 1 vertices.
Yeah,
Okay.
so I think the picture I had in mind is this. So this is, let's say this is 0 and 1. And then D minus 1. So this is 2D plus 1. And if I'm going to draw F vectors of those two polytopes like this, I think one goes, so this is about in the middle. I think one goes like this. And one goes like this. Does this make sense?
Yeah.
So one is lower. They have the same number of vertices. Starting from F1, P1 is lower than P2 up to the middle. And then after that, P2 is lower. So they sort of each dominate half of it.
Okay, thank you.
Any more questions? Then let's thank Lei again for a nice talk.
Thank you. Oh, and I would like to mention that this is also still a working progress. So if any of you have good idea, or any of the graduate students or undergrad students would like to join me, feel free to.
Thank you. So that's the end of the official talk. But if you wish, we can stay for a few minutes and continue chatting.